Okay, so we are now discussing the modeling of operational amplifiers. There exist so-called macro models, and these models, it's a kind of high-level model of an operational amplifier in which they try to model all aspects of the operational amplifier, all performance aspects in one model. An example, and I don't know if this reference is used in the book, but an example is found in, for example, this application note of analog devices, and here you see early I think this is from the 70s, macro model of an operational amplifier. And you see there were transistors used in this model and all kind of controlled sources modeling the poles and zeros of the amplifier. And here some diodes and voltage and current sources modeling the current and voltage drive capability of the operational amplifier. The problem with these models is they want to model everything at once, everything. So the noise, the high frequency behavior, the drive capability, the slew rate. And here you see in the early models, it was quite simple and can be errors in the model. For example, normally an operational amplifier has, let's say, 5 basic terminals: a positive supply, a negative supply, an output, and 2 input terminals. But here you also see ground. So there's current flowing to ground, and according to Kirchhoff, then the equations must be different than if there was not ground, if there weren't ground. So the output is delivered by a source to ground. This is later on corrected in a more sophisticated operational amplifier model from Analog Devices, this article, a suggestion in which you don't see the ground node anymore. But unfortunately, if you apply a macro model for your simulation, you don't know what is in there. You don't know, there's not like a MOSFET or a bipolar transistor, a kind of universal model that is used by everyone. So you don't know if there is current flowing to ground while there should not be any current flowing to ground. In most applications, that is not a problem, but if you make specific applications in which you take the power supply current as output, then it might be the wrong model. Another thing is that these models can become so large that they, let's say in an evaluation version of SPICE, they don't even fit. You can't even run them. And another thing is usually they're inaccurate. For example, here you see in this model that the voltage offset, so the error, usually you want to have 0 volt at the input, giving you 0 volt at the output, but of course there is an error due to technological limitations, and there can be an offset, but the offset is modeled as a fixed source, while it is some kind of random thing that remains, a random error that remains after you have tried to make a 0. So that's a little bit the danger of using macro models, and what we want to use often is specific models. So suppliers provide them. It looks like simple, but you have to check if they're correct. Not all performance aspects has been modeled, so you have to look into the explaining text of the model. Some have not been modeled correctly. There can be current flowing to ground, or the noise is not correctly modeled, or the output impedance is not correctly modeled. And here always the fact is that equivalent offset voltage is modeled with a fixed voltage source, current with a fixed current source offset, while it is some kind of random error that remains after you have tried to make these errors 0. So that's what I told already. And some of those models are too large for evaluation version of simulators. So what you need to do is you build a test circuit with the model and simulate a circuit from the datasheet of which the performance has been guaranteed, of the test circuit for the specification. But most people don't do that. So I didn't do a simulation. Maybe we will add it later, and because I want to look at a macro model that does a lot of errors, and that will cost some time. So this is about the macro model, and we are going to use another technique. Let's say if you are going to do the noise design of an amplifier, we want this amplifier over the frequency band and operating range for output and input signals of interest, we want it to behave, let's say, ideal, in an ideal way. And only one aspect we say, now this is not ideal, and this in this case would be the, for example, if we do noise, the noise. And if it would be the bandwidth, then we need a small signal dynamic model. And if it will be the offset, then we need a model for the offset. So every performance aspect requires its own model, and then we can really design or find step by step the parameters that we need for our application. So we are going to create our own models, and there are a few examples that I want to give in this lecture. So first of all, why do we do why do we do this? I told you already, not everything needs to be modeled. And some things are just, let's say, too simple. If your operational amplifier has a output voltage limitation, if it operates on plus and minus 5 volt, but it cannot deliver more than plus or minus 3 volt, then you can still use a linear model, because you just simulate the result and you say, oh, the output is 3.5 volt, so it will clip. It cannot work. You do not need to model it, because the modeling of the nonlinear behavior and this clipping behavior is seldom correct. It's not, let's say, how the real transistor-based device will work. For that, you would really need transistor-based models, and they are very large and often not supplied. So that holds for, you just plot the voltage and the current versus time and see if your maxima exchange the limit of what it should be able to deliver. Some things, and I already told you, need to be modeled in a statistical way. Let's say the offset is not a DC error voltage. It's an error voltage that differs from one operational amplifier to another operational amplifiers. So if you have two op-amps in your circuit of the same type, then you could maybe cancel offset if you use the macro model, because it's just a fixed source. But if you would use a statistical model, it would be added somehow. So we need another model for that. So SPICE can perform Monte Carlo analysis, but SlideCap has statistical description methods, even symbolically. Monte Carlo means you can say the offset source has some tolerances, but then you have already selected an op-amp and you are going to check if it works with this op-amp. What we want is, can we refine the requirement for this statistical behavior? And then you need to have a symbolic simulator. SlideCap provides you a statistical description that works also for symbolic simulation. So this is, of course, what is behind it. The offset voltage and currents needs to be zero. You try to make them zero. You want to give them a mean value of 0, and usually their 3 sigma value is specified. So 3 times the standard deviation is considered as a maximum or minimum. And the same holds for input offset current and input offset voltage, sorry. And the bias current has a non-zero value, because you have some kind of P device or N device at the input, and it needs either to have a source, a positive current in it, or a negative current flowing out of it. And for each simulation, you don't need to model all aspects together. So we are going to do orthogonal design, and each simulation uses its own model. So small signal noise analysis, we need a noise model. DC analysis, we need some statistic model for that. And we can do pulse zeros. We want a pulse zero model, and we want to have dynamic frequency response. All this kind of things can be done with our own model.